All right. Good morning, everybody. Let's begin. All right. So you have one more homework assignment. It's due on Thursday. And then the week after that, we'll have our final exam from 10:15 to 12:15. That's a little bit more time than we usually have for our exams. Our exams are generally 75 minutes, so we'll have 120. That just means more opportunities for you to distinguish yourself. I guess what it really means is, sometimes there may be 10 topics on a test and you only get tested on 3 of them. And if it happens to be maybe the 3 topics that you knew less than the other 7, then you're getting a disproportionate penalty just by random chance. So hopefully there'll be less of that for the final exam, because my intention is to include a greater number of problems, and some of them will be smaller in size. Now, as for the weighting, it's a cumulative exam, but more of the points are going to come from the material that is included since the second midterm. And so I haven't written the test yet. I don't know exactly how many questions there will be or exactly what the percentage breakdown is of the new material versus the old, but more of the points will come from the stuff in Chapter 7, and then on Thursday of this week we're going to briefly, just in one lecture, delve into some of the topics in Chapter 8. Did you have a question?
Yes. On the old material, how likely is it for you to test this on the things we've already been tested on?
It's perfectly possible. Yeah. So this class is naturally cumulative, and so the ideas of forces, momentum, continuity equation, pressure, fluid properties. It's impossible to write a Chapter 7 question that doesn't also use continuity, or the influence of Bernoulli's is really pretty direct in Chapter 7. So, I don't remember whether I gave you an Euler's equation or a Bernoulli's equation on the second exam, but I probably wouldn't give you the exact same kind of question in the final. But all those topics are still fair game. So, yeah. If you have questions as you're preparing for the test, I'd be glad to have you stop by during my office hours, or you can send me an email, and I'll try and answer you as quick as I can. I'll provide the same equation sheet that you've been given for the rest of the semester, and so you don't need to provide any kind of formula sheet for the test. You should just come with your pencil, your calculator, maybe an eraser. But,
a really big one.
Yeah. All right, so we're going to continue talking about the energy equation. And let's begin by looking at an interesting YouTube video that identifies a low head power generator. That's pretty interesting. It's something I'd love to have at my house. Seems pretty cool. You can see that, let's see if we get a direct view of the blades without the logo in the way. There was one of them. Oh yeah, here we go. So ordinarily, the types of hydropower setups that we've been talking about so far in this semester have been some elevated reservoir, and it was connected to a pipe. They're called penstocks, where at the end of the pipe is a generator, and then discharging from that generator is a lower reservoir. And so the way that we calculated the power that was available, the power equation, is the flow rate times gamma times H sub T, where the turbine head is the elevation difference between the two minus any energy losses, like through the pipe or any local losses. So H sub T was largely driven by the elevations. So it's Z1 minus Z2 minus the head losses. So that's how much head there is. And so it was using potential energy to generate electricity. Because remember, energy can be in 3 places. It can be as pressure, as elevation, and as velocity. And so When you've got some elevated water, that's potential energy. By the time the water gets into the pipe just upstream of the turbine, it's got a high pressure because the turbine's a lot lower than the water surface is, and so it's still potential energy. And then as the water flows through the turbine, what we have is an immediate drop in the amount of energy because there's a big reduction in pressure as the water goes through that turbine. The point is, the penstock, that pipe that connects the turbine and the reservoir, it's an enclosed channel. This isn't an enclosed channel. The way that this is generating electricity is a little bit different. It's kind of like a wind turbine in a way, where it's using the velocity of the moving fluid to spin the generator. And so here it's got these vanes that are probably shaped in a very similar way to the shape of a wing, so that it's able to start spinning around from the movement of the water. And then it's, rather than using pressure or elevation, this is usable in a low head environment. And they were showing it like in some coastal plain. One of those pictures, where was that one where it showed them? Oh, I guess it's this, yeah. So they're standing, it's a flat area. So that there's no elevated reservoir. You don't have to build a dam. There's no risk of a dam collapse or failure. There's no risk of cavitation like there is in the case of a big, large-scale dam and reservoir situation. So this is just using the velocity of the moving water. So it wouldn't be very good like in the Mud River. You know, those slow-moving, quiescent streams that don't have very much velocity head, you're not going to be able to generate much electricity. It also wouldn't be very usable, very worthwhile in a reservoir, in a small watershed. You know, if you only have 20 or 30 acres upstream of this thing, then there would only be water going through the channel in the immediate aftermath of a rainfall event. So we're kind of picking where this would be best suited to. It's probably best suited to mountain streams with a large upstream area so that it's always, water coming through there when you're going to be needing the electricity. And so melting snow is a really good source of a consistent water flow, because as the summer continues to warm up, the snow continues to melt, and so mountain streams are probably the best application here. But it's a really interesting application. One of the challenges of this is that you can see they've got it bolted down. They're not just throwing it in there attached to nothing. Otherwise, it can't just be dangling by the extension cord. It's going to get washed away. And so they somehow have to anchor it to the bottom. But when the flow rate is really high, that bed load, as it's called, the rocks and the rubble at the bottom of the channel, that can start to move around a little bit. And so there is a risk that you're going to have rocks encountering this device. And so I hope they made it really sturdy so that it can get pushed around and maybe even covered by the bed load when the flow rates and the flow velocities are so high that it starts to move the rocks at the bottom of the channel. But I thought it was a cool idea. It's something I definitely would love to have. So we're going to continue talking about power today and flow through a pipe network. So before we get into that calculation example, let's go over a couple of key ideas that are wrapped into this assignment that you have due on Thursday. We had to rush through the last couple of times that we've done the key ideas, so let's do them now so we don't have to rush so much. All right, so this is exactly that scenario that I just drew on the whiteboard. An elevated reservoir connected to a penstock that goes to a turbine and generator. So what we know is that the elevation difference between the upstream reservoir and the downstream reservoir here is 34 feet. And if I'm not mistaken, this is a mixed units problem, which can make it a little bit tricky. So we've got 34 feet of elevation difference, and they want you to tell them the power in kilowatts that can be generated. I got to fix that. Well, all is well in the universe now. All right, so it can be generated if there's no head loss, 100% efficient. So for this first part, you're just using the power equation, but how does the power equation work when we are in traditional units, like this 34 feet? Well, what you could do is you could change the 34 feet into meters, and then let's see, the flow rate. On this problem, anybody have the book handy? Because I'm wondering if they define the flow rate for you in terms of traditional units. So problem 758.
I used 1.4 cubic feet per second. I think that was given.
They give it to you in terms of cubic feet per second? Let's see. Problem 58. Yeah, they tell you 1.4 cubic feet per second. They also tell you the temperature of the water. Yeah, so the temperature of the water is given and the flow rate. And so let's add that to the slide, that Q is 1.4 CFS and T equals 40 degrees Fahrenheit. And they tell you that so that you could look up the unit weight, and so the gamma in those units. Now, a foot-pound is 1.356 joules. And I give that to you because if we look at the units in the power equation, if you have Q in terms of cubic feet per second, then we've got cubic feet per second, and then gamma in the traditional units are going to be pounds of force per cubic feet. And then the turbine head that can be extracted if there's 100% efficiency and no head loss, then that would be 34 feet. But the units are feet. So the units canceling out, the cubic feet in the numerator and the cubic feet in the denominator cancel out. So what we have is a foot-pound per second. And of course, you may already know that there's 550 foot-pounds per second in a horsepower, but here we don't want to know the power in terms of horsepower. We want to know the power in terms of kilowatts. And so if you have X foot-pounds per second, then what I'm saying is you can multiply that by 1.356, and now you'll know, you convert that into joules per second. And of course, a joule per second is the same thing as a watt, and then you can divide by 1,000 to get kilowatts. So this is a mixed units problem because in the end they want to know the power in kilowatts. But the process is the same. You know, the power equation is the same as we'd use, just its flow rate is in cubic feet per second instead of cubic meters. The gamma is something you're going to be looking up based on the water temperature. So any questions about this first part where you're finding the power if there's no head loss and 100% efficiency? Again, that conversion between foot-pounds and joules is, you're going to calculate how many foot-pounds there are by the power equation, and it's going to be foot-pounds per second. But if you multiply the number of foot-pounds per second by 1.356, then you're going to have some number of joules per second, and that's the same thing as watts. Okay, now the next part of that problem asks you to consider what if it's not 100% efficient, and what if there are head losses. Okay, so the first thing is the turbine head is going to be less than 34 feet because you're going to have this elevation difference, which is h. You know, this elevation difference is h, and that's not going to change based on the head losses, but now you're going to have some non-zero head loss. And so you need to subtract the 5.5 feet from the given head value of 34 feet. So you're going to be losing energy due to pipe friction, and then you're going to be losing energy in the turbine and the generator. Now the overall efficiency factor is the product of the two components. So it's going to be the efficiency factor of the turbine multiplied by the efficiency factor of the generator. So here they're saying it's 70% for the turbine, 90% for the generator. You multiply them together and you'll find the overall efficiency factor. Now here's the question. If this is the power equation, P equals Q times gamma times H sub T, do we multiply or divide to find out how much power is being generated when we've got a turbine? Is this are these efficiency factors going to mean that you're generating more electricity or less? So should you multiply or divide? We're going to multiply because it's multiplying by that fraction that makes power lower than it would have been. And so it's in the case of a pump where you divide by the efficiency factor. And the reason is that when you have an efficiency less than 100%, then that means you're going to have to put more into the pump to get out a certain amount from the pump. But here, multiplying by the efficiency factor, means that there's going to be less electricity coming out of this generator house than the energy that's going in the form of that moving pressurized water. Any questions from problem 58? All right. Now in problem 87, they're asking you to find the power supplied to the water by the pump. Okay, so you can use the power equation for that one. And so it's just a little bit of the terminology here is the pump is supplying power to the water, and you can use the given flow rate of 3 cubic feet per second. You'll be able to calculate out the effect of the losses, and there's 2 different pipe segments, but they have the same diameter. So see how leading into the pump is 8 inches and leading out of the pump is 8 inches? So you don't have to necessarily calculate the head loss in the first pipe separately from the head loss in the second pipe. You can just add up the total length and have the diameter, and you're going to need to convert the diameter from inches to feet for the units to be all consistent. And of course, you're going to need to determine the velocity through the pipe using V equals Q divided by the area. That's how you'll determine the velocity through the pipe. So the power equation would just be, you use the energy equation between location 1, where it's this downstream reservoir. Location 2 is the surface of the upstream reservoir. And you're solving that in order to determine what is the pump head required, H sub P. And so that's then the pump head that you put into the power equation. And here, I've got it in terms of H sub T, but it's essentially, equation editor 3.0. H sub P, H sub T, it's the same basic form of the equation. And in this one, they don't tell us anything about an efficiency factor that has to be considered. And so it's just going to be whatever pump head you calculate from the energy equation multiplied by the flow rate of 3 cubic feet per second and the unit weight of water. And since they don't tell us any particular temperature, you can use 62.4 pounds of force per cubic foot. Any questions about this problem? Okay. In this one, it's interesting because we don't know the elevation of the upstream reservoir. Now we know that's the upstream reservoir because here there's no pump, and so the water has to be going from up towards downstream, and the flow rate is 16 cubic feet per second. So you're calculating how much energy does there have to be in this reservoir in order to push the water through the 2 local losses that we're going to be accounting for. And in this one, you're accounting for a local loss at the pipe expansion and at the outlet, but you're not going to be calculating any local loss at the entrance. So neglect any entrance loss, but then there is also a frictional loss that has to be accounted for. And so this time, for the frictional losses, unlike this problem where it's the same diameter, and so you can just add the lengths together, in this problem you can't. You have to calculate the pipe friction separately for the first narrow diameter pipe compared to the second large diameter pipe. So in that second large diameter pipe, you're going to have a different D, and you're also going to have a different velocity. So that's why you can't combine the two lengths together. You can't add the 200 and the 500 together. The friction losses have to be calculated separately. And so the H sub L that's listed here is going to be 4 components. There's 4 pieces in the H sub L. There's the H sub L is H sub F1, which let's say that's the pipe that has diameter 1, plus H sub F2, which is the head loss due to pipe friction through that second pipe, plus there is the local loss, H naught, which is the transition from 1 to 2. And so remember that the way that we can calculate that energy loss is it's V1 minus V2 squared divided by 2G. And then the other loss, H naught from 2 to the tank. Anybody remember what the energy loss, the local loss is when you have water going from a pipe into a tank? All these local losses are some K value multiplied by the velocity head. So what's the K value for discharge from a pipe into a tank?
0.
It's 1. So you lose all of the velocity head. So that is going to be V2 squared divided by 2G. Okay, so all of those head losses, those 4 components are going in here. And of course there's no turbine, so we can cancel that term out. There's no pump, so you cancel that term out. And if 2 is the downstream reservoir and 1 is the upstream reservoir, there's no pressure at either of those locations. There's no velocity in the tank, so V1 and V2 are both canceled out. So the only unknown will end up being Z1. And that'll tell you how high does the water have to be in that upstream reservoir in order to push the water through at a certain specified flow rate when it's encountering this friction and the local losses along the way. Does that make sense for this problem? Any questions? Okay, well, this is the one that we're going to work through today. Now, this is a pretty complicated system where we have water in a source reservoir, and before it gets to some building, and we know the elevation of the top floor in the building. Before it gets there, it's encountering pipe friction losses and local losses. And so it has an inlet of a pipe where the pipe is protruding into the tank. And that's a special case where the K value for a protruding pipe is 1. And then we have a couple of bends where the K values for both of those is 0.4. And the Darcy-Weisbach friction factor looks like it's 0.019. That's just given, rather than having to get it through a Moody diagram to determine that. Excuse me. So let's calculate, and by let's I mean you calculate how much pump head is required to get the water at a flow rate of 580 liters per second through the entire 2 kilometers. Now it's 2 kilometers from the reservoir to the outlet. And you'll notice this outlet, the water is just spraying off into midair for some reason. Maybe there's a reservoir at the outlet of that we're not seeing. But it's 2 kilometers long, and we want to find out how much pump head is required to do that. So be careful when you're canceling out the terms that when the velocity is moving, you don't cancel out the V2 term. So calculate the pump head, and then assuming the efficiency of 58%, then let's try out the power equation. That's not written there because I didn't have enough room, but here I'll write the power equation on the whiteboard. P is the flow rate Q times gamma times H sub P, and then in the denominator is the efficiency factor. We're going to be dividing because this is a pump. And then part C says if there's a building part of the way, only 1.1 kilometers, so you're going to have to calculate some new friction loss amount, then how much water pressure is there at the top of the building? So P2 is going to be unknown. And what we'll assume is that, let me show you what the pipe network looks like. There's the water that's going up to this hill, and then here's the building that's on top of the hill. So there is a pipe that goes up, and calculate the static pressure of the water in that pipe at the top building. So that means if it's the static pressure, then V2 will be 0 inside the building. And so you'll just be solving for P2. All right, so I'm going to stop talking, give you some time to think, calculate, collaborate with your classmates. We know the diameter, so you can get the cross-sectional area. You know the flow rate, so you're going to be able to calculate the velocity. You'll be able to calculate the head losses, the local losses. So you've got everything you need to answer these 3 questions. Okay, let's check the answers to A and B, just to make sure that everybody's on the same page before we go on to part C. So, all right, so here's the scenario. We've got this system where the water's flowing from 1, and the logical place to assign as 1 is the surface of the origin reservoir, because we know lots of things at that surface. We know its elevation, since that's given. We know that the pressure is equal to air pressure, 0 gauge, in other words. And we know that the velocity of the water at that water surface is 0, because it's such a large tank that the water level probably isn't going down in any sort of meaningful velocity. So we know lots of information at 1. And 2 is at the discharge, where we're given an elevation, and we know that the water is still moving at 2. So unlike a lot of times where we'd say the velocity at 2 is 0, here we know that the velocity at 2 is still whatever velocity is specified to be going through the pipe by virtue of this flow rate. So when you go through all the calculations, what you should find is that the velocity through the pipe is 2.954 meters per second. And then if you put that into the friction loss equation for 2,000 meters of pipe, then we're going to experience 33.8 meters of head loss due to pipe friction. And then the minor loss, oops, I called them minor losses. The local losses here actually are pretty minor, because if you look at the magnitude of those losses, 0.8 meters because of the bends, that's just tiny in comparison to the friction losses. So rearrange the pump head to solve, rearrange the energy equation to solve for a pump head, because here we can cancel out all of the terms where there's either no velocity, no pressure, there's no turbine, but there is a pump. So we rearrange that equation to solve for H sub P, and what you should get is 50.44 meters. So how many people got this or approximately this? All right, good. Yeah. Now it really matters on problems where you're going to be squaring the velocity. It matters that your velocity isn't rounded off. So I'll emphasize again, it's a good habit to leave all of the precision in your calculator. You know, when you're solving for the cross-sectional area, don't round off the 2 digits. Just keep all of that accuracy in the calculator, so that then when you divide by that area to get the velocity, you have all of that accuracy in your calculator, so that when you square it, you're not over-magnifying some round-off issue. So since we're going to be squaring the velocity, it's especially important to have some accuracy. So H sub P 50.44 meters, and therefore we would divide by the efficiency factor in the power equation. And I got a good question about units. So let's remind ourselves how the power equation works. We've got cubic meters per second, and then with gamma we get newtons per meter cubed, and then with the pump equation, with H sub P, we get meters, right? So we cancel out the cubic meters in the numerator and the denominator, so then that leaves us with Newton meters per second. And of course, a Newton meter is a joule, so that's joules per second, and joule per second is watts. So what comes out of the power equation is watts. You can see that when you divide it by the efficiency factor, that the number of watts required is 494,863 watts. And then I round that off to 495 kilowatts. Okay, the efficiency factor. Why are we dividing? It's because if it was 100% efficient, it would use less electricity than if it's 58% efficient. So if it was 100% efficient, it would need less watts. And so since it's not 100% efficient, we know it's going to require more watts than if it was perfectly efficient. So we can't multiply by the efficiency factor, because if you were multiplying due to some inefficiency, then the number of watts required would look smaller than if it's perfectly efficient. But here we know that we're going to need more, not fewer watts, and that's kind of the reminder of why we divide by the efficiency factor. All right, now in the second part of the problem, remember the setup is that it's not the full 2 kilometers. So you're going to have a different H sub F. Your local losses will be the same because all of these K values are prior to the building. But now your H sub F is only going to apply to a length of 1,100 meters. So you'll need to calculate a different H sub F. And then the other factor that's different is we're assuming a static condition in the building. So there's some pipe coming off of the main line that feeds water up to the top surface, and so V2 is going to be 0 in this part C. Okay, let me give you a few more minutes to make sure that you have your best guess to the water pressure that we're going to experience at that building. Okay, so some things are the same, some things are different. This pump is still working when we go between the reservoir and the building. And so H sub P is the same as it was in the first case. You know, the water is still going at the same velocity, it's just we're looking at a different spot. So we're looking at a spot that hasn't yet experienced 900 meters of pipe friction. We're looking at a spot that is a higher elevation than the discharge was at that open air location. So some things are different, some things are the same. So let's look at the solution here. In part C, the water pressure at the top of the building. So 1 is at the tank, 2 is at the top of the building. Now the pipe friction only includes 1,100 meters rather than 2,000. So the H sub F is going to be 18.59 meters, but the local losses will be the same, 0.8. The pump is still operating the same as it was before, so 50.44 meters of pump head. So this is how we would rearrange the energy equation to solve for the pressure at 2. Look at what we've canceled out. The pressure and velocity at 1, and the velocity at 2, and of course there's no turbine. But all of those other factors are going to reduce how much pressure there is. And so what's causing the pressure at 2? Well, the pressure is caused by the pump and the elevation at 1. But all of these other things are going to reduce how much pressure there is. And so if the building was somehow jacked up, and if the building is raised so that Z2 gets bigger, then that's going to reduce the amount of pressure that's available at 2. And the friction losses also cut into how much pressure there is. So if the pipe was even longer, or if you change that, if you reduce the diameter of the pipe, those things could potentially increase the friction losses. And likewise the local losses, since the velocity would go up. if the pipe diameter were decreasing. So here's the general form of solving for the pressure at 2, and when we substitute in the magnitude of all of those values, so we have the initial pump head that's being added, the elevation differences, the friction losses, the local loss. So the pressure is only going to be about 56 kilopascals, and that's too low. Most municipal regulations would require that the pressure be quite a bit higher than that. About 240 kilopascals is taken as kind of like a standard minimum pressure under normal conditions, and under like a heavy fire load, like if water's being taken from a pipe network due to like an emergency event, then maybe they could tolerate 140 kilopascals. But this low, and now you've got the concern that the potential for backflow exists. And backflow is actually when you open up a valve and instead of water coming out, it can start sucking things into the pipe network. And so it's a bit of a health hazard if like the pipe fractures and then the surrounding groundwater goes in instead of water going out. Or if you think about you have a hose connected to a swimming pool, you know, maybe there's a swimming pool on top of the roof. And if you open up the hose and the water starts sucking from the pool into the pipe network, then that can really contaminate the water and cause some environmental and health concerns. So that sometimes happens during power outages around here. You know, there are people who live on hills, and when the power is out and when the pumps aren't running, then they could open up their faucet and it starts sucking air in. So that's sometimes why they'll start up a boil water advisory after a power outage in like hilly terrain. So are there any questions on part C of this example? All right, let's take one last look at these announcements before we finish a couple of minutes early. The homework 7B is due on Thursday, and we've gone through a lot of those key ideas on the assignment, but let me know if you have any questions. And then our final exam is now just 9 days away. Actually, let's see. Yeah, 9 days from now, you'll be finishing up. So that'll feel good. All right, that's it for today. I'll see you next time.